Hello, everyone. I'm really happy to be today. I'm Denys.
And I'm Lucas, and today we're going to talk about Scala Native.
So Scala Native is this weird research project that we announced a year ago at Scala Days 16 in New York. To be honest, I didn't expect people to respond too much to it because, I don't know, it was weird. But people somehow were super interested. And the core idea of the project is just a very simple concept. And the concept is, let's compile Scala ahead of time without the VM. Let's just compile it to native code straight away. And the best way to do it right now is through LVM compiler infrastructure project, and it's amazing. And this project is developed by EPFL and Scala Center, but not just these two entities, but we've got amazing number of contributors in past year. We've got 55 contributors, and like most of them are external, and I have never even met them in real life. We closed 383 pull requests and fixed 246 issues and did 3 releases already. And I would like to thank everyone who contributed to Scala Native ever. You are awesome. Even if you did a minor typo change, it's amazing. I'm really thankful. I think the project wouldn't be there where it is right now without you. So just a bit overview of what happened in the past few months. So we released a very first, very previewy release, which was called 0.1 on March 14, 2017. It was first release, and the criteria we used for when to do it was we wanted all of Scala language to be supported, even weird special features like structural types, which people don't typically use, but we still wanted to claim the full language because that's a big deal. We also worked a lot on SBT integration and making sure that SBT projects, existing cross-platform SBT projects, which were previously cross-compiling against Scala.js and Scala on JVM, can seamlessly be ported over to native without many changes. And lastly, we need enough core libraries to get the standard library working and enough core libraries to allow for simple projects. In 0.2, we continued. So 0.2 was released slightly off 6 weeks. So release every 6 weeks, next numbered release. So 0.2 was mostly focused on improving the library story. And we spent a lot of time on file I/O from Java I/O. We did regular expressions from Java util regex, which was a pretty big deal because many operations on strings internally rely on regular expressions. And first 2 were contributed by guys from Scala Center, and they're pretty cool. We also did event loop-based features, so it's similar to features in Scala.js. So we have one hardware thread, and then we schedule features on one hardware thread, which allows for evented applications. And now, essentially, what this talk is going to actually be about is it's going to be about our upcoming release, which is tentatively scheduled for next week. And the main problem we were trying to solve, and like the only problem we really want to solve in this release, was this issue, which was opened a bit more than a year ago. And the issue is called better GC. And to understand this issue, like it takes a bit of context, but essentially the question is, what's the better GC and where is it going to come from? So to understand why we need better GC, we first need to understand what do we have at the moment. So right now, our current garbage collector which we shipped in 0.2 and 0.1 is BoemGC. So BoemGC is a conservative garbage collector. It was originally designed for C++ environments where compiler doesn't really know much about your program, where type safety is a very remote and distant concept. And it was a very good starting point because it let us postpone GC as a problem for a while, and it just works. But the only problem we have with it is that it's conservative. So what does this mean exactly? So conservative GC works in environment where it doesn't really know that much about your program, so it really has to guess a lot. And there are like 2 varieties. So there are conservative GC which just handle conservative roots, but still have precise type information. And there are fully conservative GCs which neither have information about the roots or information about the allocation. So the way we were using Boehm before was fully conservative GC, so it truly did not know at all anything about the semantics of Scala or the way objects are laid out in memory, so it had to guess quite a bit. And of course, this guessing is not free, so the more you guess, the more time it takes to GC. And to understand basically what kind of overhead it had, we ported some benchmarks from SMAR. Are we fast yet? So it's an excellent repo which contains a nice, well-rounded set of benchmarks for the test standard high-level object-oriented features like virtual dispatch and high-level features, not low-level features. And essentially, yeah, we got some numbers, and if you just don't have anything to compare to, yeah, it's just numbers, which are basically the baseline, so it's not very useful. So the first question we asked is, how slow is it really? But comparing to other languages or other implementations isn't really fair because you cannot really compare GCs in isolations because GCs are tightly coupled with the language implementation and you cannot just easily take it out. So Boehm is an exception, but all high-performance GCs are extremely tightly coupled with the runtime and the compiler they're built for. So it's really hard to compare GCs, so you have to have multiple GC implementations on the same language, on the same compiler to truly be able to compare garbage collectors. So we had to have some kind of baseline, and the baseline arrived in 0.2, and the baseline is called native GC known. And essentially what native GC known does, it completely disables garbage collector. It might be a bit weird of an idea, but it's actually rather interesting for some use cases. So it's also the simplest form of garbage collection because there is no work done to collect garbage. You just allocate memory indefinitely, and that's it. So you're never free. And essentially, this is actually practical for some short-lived command line tools, like maybe Scala FMT, where you don't really care about memory management too much. You just allocate a bunch of garbage, and it's done in less than a second. And also, it's sometimes used in industry for applications with insane requirements for predictability, because GC does add this degree of unpredictability to your code, because you never know when it's going to kick in, you never know how much it's going to take, and so on and so forth. Like, for example, as far into the past as in 1995, there was this interesting discussion by Kent Mitchell, who was doing some consulting for a project that was making military missiles in ADA. And ADA is high-level language, which is still used in some fields like aerospace. And essentially, the problem was he found memory leak. And he was really trying to understand, like, how come this is going to be shipped in production, like, soon. And the answer he got is that they measured precisely how much it leaks and just put enough memory so that when rocket hits the target, it just garbage collects, basically. Yeah. And even more mature and more modern programming languages and VMs like JVM are considering this as an option because it's actually a very interesting baseline for comparisons. So for example, there's this GEP draft for JVM. I don't know what its current state, but essentially the idea is the same. Just have a mode for GC that doesn't GC, and it's actually pretty cool. So needless to say, the main interest we had for it was to have some baseline performance numbers that will tell us and show us how much do we really suck on GC. And here are numbers that compare no GC and Boehm GC. As you can see, it actually gets pretty bad on some benchmarks. It gets all the way to 5x slower with Boehm GC versus no GC. And needless to say, it's pretty bad. And to be honest, with Boehm GC, I really don't know how fast Scala Native is because it's very unpredictable and it's really hard to tell. So obviously, this basically frames the start of the discussion of why we need a better GC. And the answer is because it's truly bad. So it's typically, on average, like twice slower than no GC, which is like pretty bad. So the question stands now, we need native GC colon equals something, what is going to be? And the something is actually, there are many, many different solutions, and the design space of solution is actually pretty big. A very oversimplified and probably not correct version of how GCs can be partitioned by design decisions is here. So you have, I picked like 2 accesses. There are probably like way more in GC space, but just 2 accesses that we care about at the moment is First axis is movability of the GC. Does the GC move objects around? And the second axis is the one we've been struggling so far, is the GC conservative or precise? Essentially, you have two axes, and only things above a diagonal are possible. So, for example, stuff in a bottom right is not possible, because for always moving GC, you must have a fully precise stack. So now we have this like two camps. So camps in the bottom is a standard trade-off space for GCs and VMs. So the core kind of foundational, like for generational GC, is copy in GC. So typically you see early generation copy in GC and second generation mark and sweep or mark compact or some weird hybrid of the two. Is basically the quintessential standard generational GC formula. And the main point of copying GC and why copying GC are actually a good idea is the fact that by copying, GC can optimize the application for best memory locality. And because it compacts, it can also bump allocate most of the time. So bump allocation is the fastest way to allocate that we know today. But of course, it's not free. So fully precise GC has non-trivial engineering costs to support fully precise stacks. And it also requires compiler to be very careful about GC references versus unmanaged references. And essentially, it is possible on LLVM, on latest version of LLVM, finally start to get reasonably good support for fully precise GCs in latest releases. But old releases still have outdated GC infrastructure, which we are not going to use. So maybe this is an interesting place to be in the future. But right now, LLVM doesn't, at least old versions LLVM, which our people typically use, which come bundled in Linux, typically don't support this yet. So, and now you have a separate kind of camp. And separate camp is of non-moving GCs. And here you typically have some kind of reference counting hybrids and some kind of mark and sweep hybrids. And this is the most standard pick for AUT compilers, because non-moving GC actually simplifies GC compiler interface, and it gives compiler more freedom to do things, because especially on a fully conservative or conservative roots solutions, you don't have to tell compiler what's going on. And this is basically the space we want to be. We don't really want to integrate with LLVM too far. But of course, it's so there are two standard solutions. The first one is reference counting. Reference counting is a solution that's used by many languages right now in AUT space. And it's basically what it does is, so every object has a number of references from other objects or stack. And this is a simple solution. It's really easy to implement. But to make it practical for Scala, you will need something more advanced. Like you would need to have a special cycle collector to trace suspected cycles, because reference counting on its own, core idea, cannot handle cyclic data structures, because let's say you have two objects, they point to one another, they will always have a non-zero reference count, which never goes to zero. And apart from that, it also requires constant overhead on the application performance because of the extra work necessary to constantly keep this reference count up to date. This work is not there for trace and garbage collector, because for trace and garbage collection, you never have to update anything during application time. You only update things during actual GC. And then there is one more simple idea, which is a quintessential, decades-old mark and sweep garbage collection. And the idea, again, is very simple. You just traverse the heap, you mark every single object which is reachable, and then you go through heap once again, and you sweep all the objects which are not reachable to some data structure like free lists. And both GCs actually are very problematic in some ways because they're non-moving. So it means GC has like very little freedom to keep fragmentation low, and it has no freedom to improve memory locality at all, because the protocol is the GC must follow is it never moves objects in memory. And typically, it's also backed by free lists, which are not competitive in terms of allocation performance compared to bump allocation. So now we are basically, so we have some kind of background, so we understand what kind of GCs people typically use, and we are probably in the worst possible combinations of two features at the moment. So we have fully conservative, non-moving garbage collector, so it's like truly bad. And you've seen the numbers, it can get up to 5 times slower compared to not having a garbage collector at all. So the first question is like we have to move in this design space somewhere, and the first thing we decided to try on is to see how much overhead does fully conservative versus conservative roots has. Because for fully conservative, you don't know neither the stack nor the layout of things in memory. So you really have to guess a lot. And the first thing we want to try is to go to the left. And to the left means to give GC more information. And this is where our first experiment, mostly precise mark and sweep comes in. And around like February, Lucas was looking for a project to work on, right? And I suggested for him try mark and sweep. It shouldn't be that bad. It should probably beat Boehm like easily, right?
Yeah, it looked kind of scary, but you convinced me, so I started working on mark and sweep with conservative roots. So mark and sweep has been around forever. It's really old, but it's rather simple. So it has two phases. The first one is the marking phase, which is here to identify the live objects. And then comes the sweeping phase, which goes through the heap to collect the garbage and return it to the allocator for new allocation. So what does it mean to have conservative roots? So conservative roots means that elements on the stack, for example, can point anywhere. They can point outside the heap, but also inside the heap. And even more, inside the heap, they don't only point to object headers, but they can point anywhere. So we have to handle them carefully to resolve the header of the object. So for inside the heap, because the heap itself is precise, the compiler emits information for every type that is used by the GC to know exactly which values are references and which are not. So in our case, we have 3 types of roots. The first ones are registers. They're not on the slide because they're simply dumped onto the stack. Then we have the stack. And finally, the modules. The modules are precise. They are the Scala objects. So precise means that they're either null or point exactly to the header of an object. So now let's look at the marking phase. So what the marking phase does, it goes through the roots and does a breadth-first search traversal of the live object graph. So for example, here the first element points into the heap, and we follow it, we mark it, and afterwards we need to mark all its children. So in this case, there's only one. We mark it, and now we're done with the first root. So we go to the next one. We follow the pointer, mark it. Here we have 2 children, but the first one's already marked, so we stop here. We don't have to do anything. And we mark the second one. Same thing for modules. So we follow it, mark it, and same thing with the children. So now we're done with the marking phase. So our heap has some objects that are marked and some that are not. And the goal of the sweeping phase is to go through the heap and collect all objects that are not marked to return it to the allocator for new allocations. So to do this, we simply go through the heap, object by object, and if they are marked, we unmark them, like the 2 first ones, and if they're not marked, they're now free and return to the allocator. And we do this for every object in the heap, unmark it, and so on. So this is what it looks like after collection. So all the blue objects are free and have been returned to the allocator for new allocations. So the results we got were rather interesting, but we were still not satisfied. So here you see the benchmark comparison with Boehm and NodeGC. So the average performance, or the average overhead went from around 100% to 25%. And you can see this very well on benchmarks like Tracer, which has a lot of live objects, so the tracing part, the marking part, is really expensive. But because we have a precise heap, it got cheaper. But we also have benchmarks like GC bench. And this benchmark is allocation bound. So it allocates a lot, and it still has around 100% overhead. So this is pretty bad. And the problem here is that conventional mark and sweep allocators use free lists, and free lists are slow. So we saw that mark and sweep was not the solution we were looking for.
So, and here we are. So we now have two solutions. None of them are good enough, so this is not good. So we have to keep looking, I guess. And essentially, the problem it was, as described by Lucas, is that allocation in non-moving setting is actually a bit tricky, and you really cannot easily do bump allocation. It's very tricky to pull off in a fully non-moving setting. So we kept looking naturally. So because this was like just mark and sweep wasn't good enough, even though it did improve upon Boehm, which mostly because it had more information. So the next space we wanted to try is actually this super weird and mostly not well-researched space of mostly moving garbage collection. So mostly moving garbage collection is a different, it's like a trade-off between fully moving and non-moving. And essentially the idea is GC can move stuff around unless the objects are pinned. So you split objects in two types, the one which can be moved around and the ones which cannot be moved around. And essentially everything referred from the roots, you can still keep the roots conservative because you can pin those objects down and make sure that stuff referenced from root never changes location in memory. And there are two GCs, actually probably more, but essentially two well-known solutions in this space. So the first one is called Bartlett, and it's a hybrid of a copying GC for mostly moving use case. And it's the underlying GC technology for Safari and WebKit, so it's actually pretty usable. And it's based on the work by Joel Bartlett on compacting garbage collection with ambiguous roots. But another one that also exists is called IMIX, and it's a marked region garbage collector. Marked region, you probably never heard this term before, but it's actually its own family of garbage collectors, which are not that well known because they've just appeared like less than 10 years ago on the scene. And essentially, it's a very simple idea, and it's also, like the original paper, offers one-pass defragmentation, which gives it this compacted nature. So the original was from the paper IMIX, a marked region garbage collector with space efficiency, fast collection, and data performance by Stephen Blackburn and Catherine McKinley. And we really like this idea because it was quite close to and quite workable and easy to do based on mark and sweep prototype we had. So it took us, what, like maybe 3 weeks to do a first hack of a prototype?
Yeah, like 2 or 3 weeks. So the core idea is pretty much the same as for mark and sweep. The difference is that we have a bit more of a structure in the heap. So before we had the heap and just the objects inside the heap. Now the heap is separated into blocks. These blocks are around 32 kilobytes large, so they're pretty large. And then inside these blocks, we have lines. The lines are pretty small. They fit into like 4 cache lines. And these lines can either be free, here in blue, or allocated with objects. And the block also have 3 types, so they can be either unavailable if there is no free line in it. They can be recyclable if we have some free lines and some allocated lines, or they can be completely free, like the last one. So how allocation works here is that we do bump allocation on free lines. So this means that we have a cursor at the beginning of the lines and one at the end. And when we want to allocate an object, if the size of the object fits between these 2 cursors, we add it and update the cursor. And we do it like this. And this is very good because bump allocation helps a lot with memory locality, because objects that are allocated together are often accessed together. So that's really good. And even if we want to allocate large objects, we can allocate them on several lines at a time. That's not a problem. And once we're out of space, we're going to look for the next line that's free and do allocation. So that's it for allocation. And the marking phase is pretty much the same as for mark and sweep. The only difference is that now we not only mark objects, but we also mark blocks and lines. So for example, here on the first reference, we follow it. We mark the object, the line, and the block. We mark the child. Here, the line and the block is already marked, so we don't have to do this. And same thing with the second one. We mark the lines and the object. So that's it for the marking phase, so it's pretty much the same. But the sweeping phase got improved a lot. So here in this case, the block is marked, so we will have to go through it line by line. So here on the first line, it's also marked, so we have to go and unmark the line, unmark the object. Same thing here. But now, this line is not marked, so all at once, we just say this line is free. Same thing for here. And for the second block, because it's not marked, we don't have to do anything. It's just free. So this improves a lot. The performance of Imix was quite a surprise to us, right?
Yeah. I remember at some point when you just had the first prototype, you were like trying to really hard to figure out why did mem set 0 became so slow?
Yeah, exactly. Before with mark and sweep, clearing the memory would never show up in the profiles, but somehow now it got really slow.
So we were trying to debug it, like we're trying to figure out, are we calling mem set 0 too much or something? And it's only until we debugged it until more and actually did run the benchmarks did we see that it was actually not a bad sign. So performance improved a lot. And when I say a lot, it went from the worst case 2x to a typical worst case of like 20% overhead. On many benchmarks, it's way lower than that. And the very worst case on a single benchmark we have is, I think, around 50%. A typical average of overhead over our benchmarks is just 10%. And of course, naturally, it's like way better than Boehm, which has worst case overhead of 5x and typical overhead of 100% over no GC. So you pay for GC, but it's like tiny little cost of 10%. So it's really nothing. And I'm pretty sure this does qualify as a good GC, maybe not the best GC the world has ever seen yet, but so we really have to close the ticket now because it's been going on for too long. Yeah. Okay, cool. Yeah, we're currently on Scala Days, guys.
Show us on the screen.
You don't see it? Oh, no. Okay. It's like this. So we are at Scala Days, and Imix is pretty good, guys.
Congrats.
Okay. So this is basically what's the main kind of topic of our talk is we finally get a good GC. And this new good GC is coming as a prototype in 0.3. It's not enabled by default, but it will slowly be enabled later by default. And now you can opt in by native GC Imix. We're going to support Boehm at least as long as Imix is not a default. It will stay there for some time. But naturally, we expect Imix to be unconditionally faster, and if it's not faster than Boehm, please tell us. It should be like way, way faster. On every single workload we've tried, it's way, way faster. And there are a few other nice features that are coming in 0.3. So we get SBT testing framework integration that's being contributed by Martin Duchem from Scala Center. We have initial support from File.io and ZipJar's APIs, also Martin Duchem. And we also have very nice thing, we have smaller binaries now. So we did some work on optimizing overhead of additional metadata that we dump next to your code in native binaries. And on some pathological cases, it can be 10 times smaller, but typically I would expect like 20, maybe % smaller binaries. And that's around it for today. Thanks for listening.
How mature would you consider the project at this point? Is it production ready, a year from production, 5 years from production? Is there any estimate to that?
I'm not going to give you any estimates because estimates are hard. But the bigger the version numbers, the more stable it is, right? This is how it works.
Did you test it on large heaps, like hundreds of gigs, and
That's a
what
very
are
good
the
question.
collection times?
So the question was, how does it scale to giant heaps? So it's still a marking GC. So it has this like a typical cost of this standard stops the world marking GC has, and it does do amount of work proportional to the live heap size. So this is not solved yet. So the post times basically are proportional to the number of memory you allocate. It's not really proportional that much to the number of memory you have, because sweeping is now super fast compared to mark and sweep. In mark and sweep, sweeping was very problematic, but here it's basically just live object size essentially is that is the cost. So this is not completely solved yet. Yeah.
So given that it's LLVM as a target, what are you seeing in terms? I presume dead code elimination is possible as part of linking, and then in relation to that, what are you observing in terms of resident memory sizes of your processors running versus, say, the equivalent JVM-based program?
So we didn't truly benchmark, so we cannot tell for sure, but we have way cheaper heap typically because, first of all, we don't have copy in early generation, which duplicates memory like area twice, because it needs it like to copy somewhere, right? And we also don't have all the JIT overhead, like the typical JIT code, loaded code, optimized code, and all of the intermediate data structures that JIT compiler uses. So I would expect we have like at least like 50 to 100 megabyte like just advantage, for example, on a 512 heap. So at least like 10% advantage in terms of how much stuff you can fit in memory for the same heap size. But that's my rough estimate. We haven't truly measured how much the same code base, the same live data set takes in both JVM and native. So but I expect it to be better.
Have you done, I mean, is dead code elimination possible there through linking?
Coordination, what do you mean?
Dead code elimination.
So we do, so dead code elimination happens actually a lot. So first of all, we do dead code eliminate ourselves before LLVM. So we do a simple version of Scala.js global whole program dead code elimination. It's slightly stupider because we don't really care about code size as much as Scala.js does. So we basically trade simpler, faster, like dead code elimination, but it still happens at link time. And of course, LLVM optimizes it even further after us, but we help it by pre-optimizing it beforehand.
So I guess there are trade-offs in this IMIX GC collector. The sizes of the blocks and the sizes of lines.
Yeah.
How is that decided upon?
So essentially, so the original paper argues for 32K blocks and 128 byte lines. So lines are supposed to be very small because you never sweep on object basis, you sweep on line basis. So if your lines are too big, you will have, for example, if you have just one object in line, it will be dirty. So you will basically just keep too much memory not available for allocation. So lines are supposed to be small, and it's 128 now, and blocks are supposed to be large. And that's basically the main invariant. We haven't truly, we tried benchmarking on an older implementation of IMIX we had on different sizes of blocks, but it seems like the one picked by the original paper is a good trade-off in terms of block and line size. We might do some more when we have more real-world workloads to play with it a bit more, but I think the current trade-off of 32K and 128 is a pretty good trade-off.
Hi.
Hey.
I was wondering if you were planning any other features that would require changes to the runtime, such as green threads?
I wowould love green thread to happen, but we don't have anything at the moment, and essentially at the moment just an idea. Something like Go routines built into the runtime would be super nice, but essentially we will have save points because as soon as you have multi-threading, you will need save points to stop all the threads to start the GC. And save points can also be used for preemption for green threads. So the answer is, it would be really cool to have it. We don't have anything yet there. It looks like we have no more questions. OK, thanks for coming.